Good afternoon, everyone. I hope you can hear me, and I'm just going to my presentation real quick, and I'm very glad that you all come to see my presentation. Thank you so much for that, and I hope you are enjoying this summer also, the summer weather. So okay, so I'm just start my presentation. And the topic of my MS project was the selenium removal and pollution swapping potential of passive anaerobic bioreactors receiving coal slurry impoundment waste. So let's start. So here is an picture of coal slurry impoundments. Don't confuse with at the lake. This is actually coal slurry impoundments, which is a large engineered structure usually built into the Appalachian Mountains to contain the byproduct of coal washing process, because coal need to be prepared by washing to remove the silt, clay, and trace elements. To elaborate it more, like coal contains ferrous selenite with the presence of water and oxygen. It can be chemically weathered into selenate. And this whole process generates huge amount of liquids, the billion gallon, multi-million gallons, and which is easily set into these impoundments. So there is around more than 700 impoundments into the Appalachian region of USA, in particular Kentucky, West Virginia, Ohio, and Pennsylvania. Here you can see an satellite image of coal slurry impoundment position in USA. So why do we care about these coal slurry impoundments? There is a photograph of West Virginia where you can see here in the these impoundments usually built very close where we live in. And these impoundments contains some bad elements like, for example, arsenic, selenium, and lead. And like for here, I just stated that the selenium usually is much higher than water quality standards recommended by EPA for LOTIC system, which is 3.1 ppb. Water chronically leaks through the dams into the adjacent streams, and then which usually pose health risks to the sensitive oviparous species like fish and birds. Here is a photograph you can see which is the selenium-induced toxicity, more particular due to oxidative stress for sunfish and creek chub. We say that is facial and spinal malformation. So what would be the possible solution for that? The PAB system, which has been used for more than 25 years to remove the nitrate from agriculture tile drainage by denitrification. Here is a picture of the process, how in the field condition we can build a PAB system. The step one, excavate the trench and line with impermeable membrane. Step two, fill out with organic matter, like for example, wood chips and other organic matter. We can use Timothy hay also. And cover with liner, and then cover with soil and vegetation. Here is a nice illustration of an operational wood chips bioreactor. In the left yellow arrow, you can see the effluent is coming, and the right yellow arrow, you can see the effluent is going out. The main advantage of this system is that no energy and maintenance cost, minimal wildlife exposure, and thermally insulated by soil and year-round removal. So similar system can be used to reduce selenate into elemental selenium, but this process hasn't been extensively evaluated for selenium removal. Dissimilatory selenium reduction could be a very good solution of that, which is a two-step process where selenate reduced into selenite and then selenite ultimately reduced into elemental seleniums. Here is a photograph uh, uh, of this process where I used the wastewater to see whether that wastewater of Kentucky contained selenium reducer or not. In the left, you can see the control where is no selenium and microbes. In the middle is the selenium and microbes, which is and the right on the is the microbes without selenium. You can see the red color, which is the elemental selenium, which is a sparingly soluble and non-bioreactive solid. Possible disadvantage, which is the pollution swapping. Which is now I'm stating what is the pollution swapping is the production of dissolved nutrients, organic carbon, trace element, greenhouse gases from the organic substrate in PAB could be detrimental to water and air quality. The goals of my project was to evaluate the influence of organic substrates and maturation time on selenium removal rates in PAB system. To the evaluate of the influence of organic substrates and maturation time on production of greenhouse gases, nutrients, and dissolved organic carbon, pH, and trace elements in the effluent of PAB system, which is the pollution swapping. My hypothesis was selenium removal rates and pollution swapping are significantly related to the type of organic substrate and maturity of the PAB systems. To address this question and find out the answer, I have built PAB system using mason jar with 4 organic substrates and simulated cold slurry. The 4 substrates that I have used was wood chips, Swiss grass, miscanthus, and Timothy hay. Over the 7 months, I have evaluated the chemistry of the solution, which is pH, EH, selenium, and other elements by ICP-OES and ICP-MS. Thank you for Dr. Andran for providing me the facility. Also, I evaluated the DOC, ammonia, nitrate, phosphate, sulfate, and TOC by TOC analyzer and colorimetry method. Greenhouse gas has been also evaluated by using greenhouse gases has been also evaluated, which is the carbon dioxide, nitrous oxide, and methane using TCD, ECD, and FID detector by gas chromatography. The statistical analysis has been done using determined by ANOVA and Tukey, and the water quality indices has been done by comparing the concentration of my system with the pristine Appalachian streams to compute the overall water quality indices of PAB with different organic substrates. Now, I have selected 13 parameters that could affect the overall quality of the effluent, and I choose the reference concentration to evaluate overall the effluent quality of my system. And this pristine concentration you're seeing is like the system which is not affected by the mining activity in the Appalachian region. To calculate the water quality index, I have used the Canadian Council Minister of Environmental Quality Index, which is the function of 3 factors. One is related to the F1 is related to the number of parameters that fail. F2 related to the number of total failures during the experiment. and F3 related to the extent that fate parameters deviated from the guideline concentration. To elaborate it more, so if after calculating all the things, if I see that the score is 0 to 44, I categorize my effluent as a 4, and if this is 95 to 100, then the effluent quality is good, excellent, and which means that it's ready to release into the surrounding streams, and it's just and it would not affect the aquatic life. The first before building the PAB system, I did the proximate analysis of my organic substrates. Here you can see the total carbon. There is not much differences in here, but in case of nitrogen, you can see that Uchip has lower nitrogen significantly, and Timothy Hay has the highest. And consistent with that, the CM ratio is high in Uchips, but Timothy Hay has the significantly low. And also in here, you can see that the non-destructible organic carbon, which is lignin, which has more lignin than other substrates. My prediction was the selenium reduction, DOC carbon dioxide production will be high in TH and lowest in chips, and very little inorganic nitrogen will be released due to high CN ratio. So here in the left side, you can see a figure in the x-axis is the time and the y-axis is the concentration of the parameters, and the similar styles have been maintained all of my figures. So I hope you will understand the figure very easily. So you can see that the dissolved organic carbon concentration was significantly affected by the types of organic substrate in the PAB metric. The DOC, like for example, the DOC was significantly higher in PAB with Timothy Hay and then other substrate. I just showed the table. I just showed the table where you can see that the water extractable carbon is more, water soluble carbon is significantly higher in Timothy Hay than other substrate, which is consistent with the DOC value that I found. DOC is steadily declined with increasing maturation time and water replacements, and declines due to combination of bleaching, dilation, and decomposition. And here you can see the background DOC in Appalachia in the topmost is 2.5 milligram per liter. And in my system, the DOC concentration of PAB is always greatly exceeded the background. A likely problem is in receiving water bodies, and which is the high BOD and oxygen deprivation. Redox potential was significantly affected by types of organic substance and PAB in the maturation time and maturation time. In 0 to 1 month, the topmost figure of figure A is that the EH is rapidly declined to minus 300 MV to all PAB except wood chips. EH differences likely the reflection of organic carbon availability and decomposition rates. With increasing PAB maturation, EH values tended to decline more slowly than the initial maturation month and did not reach as low as the initial maturation month, which is the figure A. Now, the main element that I am interested, which is the selenate, right? So the EPA target concentration for Lotic system is 0.003 milligram per liter. And the result shows that selenium reduction rate significantly affected by the types of organic substrate and maturation time. During 0 to 1 month, which is the figure 1, which is the A, selenate reduction rate was significantly faster in PAB with Timothy Hay, then followed by miscanthus swissgrass and wood chips. And this is followed the similar trends of DOC concentration. With increasing maturation time, the selenate reduction rates greatly decreased in all PAB. By the 6 to 7 months, which is the figure D, you can see here, an instance and interesting things is happening in here. The selenate reduction rate was significantly lower in PAB with TH than other substrate. I will elaborate that later on in my slides. And as you can easily see here, the selenium concentration in PAB always greatly exceeded than my target concentration of which is 0.003 ppm. What is the possible reasons for this? One of the possible reason is the electron donor availability. Again, the background carbon dioxide concentration in Appalachian stream is 9 based on my research efforts. And during 0 to 1 month, the selenate reduction rates and respirable organic carbon was significantly higher in PAB with TH, which is the Timothy Hay. Selenate reduction rates and respirable organic carbon decrease with maturation time as I changes the cold slurry with each maturation time with fresh one. During 6 to 7 month maturation, low electron donor supply does not explain the lower selenate removal rates in PAB with Timothy Hay compared to other subjects. Now, what could be low pH? Now, I am again stating what is the background pH in Appalachian pristine system streams, which is 6.8. Here you can see in pH 6.7 is optimal for selenium reductase. I showed you the distributively reduction system, which is the two-step process, and the main thing in here is the selenate reductase enzyme, which is the main agent which is actually reducing the selenate and selenite into the elemental itself. And you can see that enzyme need optimal pH, which is 6 to 7. And this is supported by also my result that the pH affect folding and assembly of enzyme in periplasmic space. Here you can see the pH 4 is in PAB with wood chips and Timothy Hay could explain the low selenate reduction rates. But what could be the probable reason that the wood chips and Timothy Hay has low pH? Probable reason is the abiotic hydrolysis of hemicellulose produces acetic acid and formic acid, and fermentation also produces volatile fatty acid. And this low pH could have adverse effect on other biogeochemical process and stream biota, like for example denitrification. Also. Here you can see that thing where the pH affected the denitrification. And also here you can see that the different substrate have different pH in different maturation. But here you can also see that the miscanthus and switchgrass has higher pH. The probable reason could be the sulfate reduction. I will discuss this more in my later slides, the sulfate reduction. Another possible reason could be the diffusion, slow diffusion. So when I prepared my synthetic cold slurry, the initial concentration of selenate is 0.6 milligram per liter. And here you can see that when the bulk solution, which is the initial concentration of the cold slurry is 0.6, there could be a steep concentration gradient, and therefore the fast diffusion can happen into the selenium reducer into the and that help to diffuse the selenate to get into the periplasmic space of the cell of selenium reducer where this selenium reduction happens. But this, when after the incubation time of 15 days, usually the selenium concentration decrease into the 50 ppb, which is 0.05 milligram per liter, the slow concentration gradient or slow diffusion might happen. And therefore, I'm saying that the selenate removal rates and low concentration could be diffusion limited. The similar effect has been also found in nitrate concentrate and nitrate removal systems also. Now, let's talk about the nitrate removal of the PAB system. Yes, this nitrate rapidly removed by this near detection limit in all PAB in about 10 days, and that verify the previous notion, which is that the PAB system is good for nitrate removal. However, we have to think about that the system can remove the nitrate, but it also contribute other pollutants, which is just I just said in my previous slide that it's contributing the pollution swapping. We should not just think about the nitrate, but it can contribute other pollutant in this process. Here is an example of one of them, that is nitrous oxide released due to denitrification. The background nitrous oxide of Appalachian stream is 0.004 milligram per liter, and nitrous oxide produced in all PAB system, which indicated that denitrification was important. The nitrous oxide accumulated to higher concentration in PAB with wood chips from 0 to 2 months, and also Timothy Hay into 6 to 7 months. You can see here, and likely due to the low pH, which can inhibit the nitrous oxide reductase enzyme in periplasmic speech, like similar to selenate reductase enzyme. You can see the arrow in here, the spike of nitrous oxide release. After day 15, during 6 to 7 month period, nitrous oxide concentration in PAB with Timothy Hayes greatly exceeded the background. Now, what happened to the ammonia? Now, again, the background inorganic nitrogen in Appalachian stream is 0.81. And we can see here in that the ammonium produced right after replacement in all PAB system during early PAB maturation periods indicated that DNRA, which is the disseminatory nitrate reduction to ammonium, was probably important. And also the condition is favorable for that because the initial nitrate concentration is low. When I prepared the simulated coal slurry, it's like 10 ppm, and it has high DOC also, just I just showed you, which is favorable for DNRA according to the literature I have read. And also ammonium concentration decreased after about 3 days, which indicated the assimilation, and which is also supported by my previous data because the high assimilation. By the day of 15, in the 6 to 7 month of period, the inorganic nitrogen concentration of PAB approached the back. Now, electrical conductivity. The background electrical conductivity in Appalachian stream, pristine system, is 0.07 microsiemens per centimeter. Here you can see that the EC in the coal slurry is about 2 millisiemens per centimeter. The main cations in my electrical conductivity is the sodium plus, calcium, magnesium, potassium, and also sulfate and chloride. The EC in PAB system did not change or increase, especially for Timothy Hay, where I found that the potassium is 42 times greater than synthetic coal slurry, and the magnesium and calcium is 5 times more than background coal slurry. The EC in PAB always greatly exceeded the background. And also now get back to the now the interesting thing about the sulfate reduction. The sulfate in Appalachian streams in pristine system is 12.5, and the coal slurry usually have more sulfate than normal than Appalachian streams. That I just mentioned in here that the sulfate concentration in coal slurry is about 1,000 milligram per liter. The sulfate, similar to selenate and nitrate, sulfate reduction was also observed in the PAB with miscanthus. In after more than 1 month's maturation period, in the left side you can see that the rectangle where the miscanthus is after the initial maturation period, which is A, Then you can see the B, C, and D in the left side of the figure, that miscanthus is continuously showing that it can reduce sulfate also. And PAB with switchgrass in the month of 6, which is the cross sign in here. The sulfate reduction not observed in wood chips and Timothy hay. Possible effect could be pH, because we know that the sulfate reducer, the acidic condition, the undissociated carboxylic group is very toxic for them. So the sulfate reduction, which is a proton consuming process, are not as good as the other substrates. So that's why you can see that sulfate reduction doesn't happen in wood chips and Timothy hay. By the day of 15, sulfate concentration of PAB is always greatly exceeded to the background. And the sulfide produced in miscanthus and switchgrass could also be toxic to stream biota, and which might cause sleep and respiratory disorder in fish. Now, what happened for the phosphate? The background phosphate concentration in Appalachian stream is 0.05. During 0 to 1 month, the left side figure 1A, you can see that the phosphate concentration rapidly increased in all PAB except oceans. The relative concentration in PABs is predictable from water extractable phosphate also that I did, where the Timothy hay has the highest, followed by miscanthus, swissgum, and wood chips. The phosphorus concentration decreased with increasing maturation time. By the day of 15, during 6 to 7 months of maturation, phosphorus concentration in PAB exceeded the background also, and which might cause the eutrophication in the receiving water bodies. Let's talk about the zinc. The background dissolved zinc in Appalachian streams, the pristine system is 0.01. So when I evaluated the zinc in my system, I find out that during 0 to 1 month, zinc concentration rapidly increased in PAB with switchgrass and Timothy hay, which was predicted from the relative concentration from water extractable zinc. But the switchgrass has the highest. You can see the left side, the cross mark of the switchgrass is the highest concentration. Zinc concentration decreased with increasing solution time due to leaching and slow decomposition of organic zinc, and also it could be zinc sulfate, because as I said that in miscanthus and switchgrass, sulfate reduction happened, and the condition is good for zinc sulfate also. So it's possible that zinc sulfate can form in the system. During 6 to 7 months, zinc concentrations are below the background of all PAB except those with Timothy hay. Now, what happened to the iron also? The background dissolved iron in Appalachian pristine system is 0.22 milligram per liter. The cold slurry contained 0.05 when the synthetic cold slurry that I prepared. And I see that the first 3 days from 0 to 1 month, iron concentration rapidly decreased in all PAB. You can see the figure A, the dip of iron concentration. Possible reason is likely that iron 3 bind with lignin and cellulose that is supported by the previous literature. And after 3 days, the iron concentration increase in all PAB. The likely cause is desorption of Fe2 plus and also leaching and decomposition of organic iron. In PAB with Timothy hay, the less Fe2 absorption by lignin. So when I presented to you all the proximate analysis, we see that there's a lignin concentration is significantly lower in Timothy hay, and as here you can see that in all the month that Timothy hay have higher release of Fe2. So I'm saying that because of the lignin is less in Timothy hay, so that's why you can see that's significantly high Fe2 plus in PAB with Timothy hay system. by the day of 15, in 6 to 7 months, the iron concentration were highest in PAB in Timothy Hay and wood chips and exceeded the background. So what could be the possible consequences of that? Because Fe2 plus can get oxidized and consume the dissolved oxygen, and also it can, when it's from the iron oxyhydroxide, which can clog the fish gills, and it can create the respiratory problem for fish also. The lower in Fe iron in PAB with miscanthus and fish gills during 6 to 7 month period, and as that could be where the iron can bind with sulfate and forming iron sulfide. That's why we can see that in miscanthus and Swiss grass in 6 to 7 months, which is the figure D, the low iron concentration. And that's what I'm saying, because the sulfate reduction is happened, so might be the sulfate and iron from precipitation. That's why we can say that that might be happening in Swiss grass and miscanthus. Now let's evaluate now. For overall evaluation of my effluent, I did this Canadian Council WQI, uh, and by assessing that, I found out that in all PAB system, the maturation time, the WQI scores of water is below 25, which is categorized on that the effluent quality is very poor, and WQI scores tended to increase with time and would like to continue to improve the longer maturation time and more water replacement. However, it seems unlikely that the selenium target concentration could be achieved using PAB system because it's significantly low. Now, go back to my hypothesis again, which is that the selenium removal rates and pollution swappings are significantly related to the type and chemical composition of organic substrate and maturity and age of PAB system. I found out the selenium removal rates was significantly related to the types of organic substrate and maturity age of PAB system. The key factors are the organic carbon availability, pH, and selenium concentration. Now, in case of pollution swapping, the pollution swapping is also significantly related to the type of organic substrate and maturity age of PAB system. Some pollutants of concern are like selenium in all PAB, DOC in all PAB, phosphate in all PAB, sulfate in all PAB, NEC also in iron in wood chips, and Timothy Hay on. Now I'm based on what I learned in this project, I'm recommending something here which could be very beneficial for other researcher, which is that the selenium target concentration was not achieved during PAB treatment technology. So at this time, it is not recommended to implement into the field system. But I have an idea that lower sulfate concentration might increase overall removal process, because the selenate reductase need molybdenum, and based on the literature that I found, that the high sulfate concentration, sometimes high sulfate concentration hints the molybdenum incorporation into the selenium reducer, and the selenium reducer need molybdenum to activate the selenate reductase enzyme. So this I have an idea to remove sulfate first, and then follow the uh, same remediation technology to see whether it can reach the EPL limit, which is 3 ppb. The PAB systems were very effective for nitrate removal that I showed you, but it can contribute many pollutants that I also showed you that. Yes, it is very effective for nitrate removal, but it can contribute the other pollutants also. So what could be the, so I'm saying that, so we should use with more caution this technology. I'm recommending to characterize the substrates for organic carbon availability by proximate analysis and CN ratio. and characterize the substrate for water extractable elements, especially nutrient, major, and minor cations. And an alternative plan that also can be done for disposing the PAV effluent during the early maturation times is like mine land reclamation, because you can see that the effluent has high nutrient rich, right? It has more nutrients, so we can use this effluent for mine land reclamation as a liquid fertilizer also. So the second use could be that for this nutrient rich effluent would be crop irrigation water. So this is my recommendation. So I want to thank my advisor, Dr. Alisa D'Angelo, for her overall help in my MS project. I also want to help my committee member, Dr. Mark Coyne, Jason Ryan, and Dr. Andrea Adhat for their valuable and thought-provoking suggestions. I also want to thank my Tammy and Megan for my analytical help, especially ICMS and ICPOES. And last but not least, I want to thank the University of Kentucky for providing me the opportunity to do and learn science. So thank you all for listening and with my presentation. And if you have any question, so just I'm happy to answer.
Nice job, Anik. This is Chris Matoka here.
Okay.
I was curious, did you speciate the iron? You talked about the possibility of iron sulfide precipitating at the longer maturation time. So I was just curious did you measure just total iron, or did you actually quantify iron too?
I measured the dissolved iron. I didn't specificate it. I just only measured the dissolved iron from the effluent, and based on the literature, I made some assumption that what might happen in my system. Okay.
All right. Thanks.
Thank you for the question. Do you have a question, guys?
Hello, Mr. Anik. Can you hear me?
Yeah, I can hear you.
Thank you for your nice presentation. It was well explained. I want to learn more about your future plan about sulfate reduction to increase the availability of molybdenate in the system and to ultimately increase the selenate reduction availability.
Okay.
So, could you please elaborate on this?
Actually, the recommendation, so it's in the recommendation section. Yeah, let me share that first. So yeah, can you see my slides right now?
Yes, I can.
Okay. Yes. So in this section, the recommendation section, I say that lower sulfate concentration might increase the selenium overall removal process. So I recommended this this overall technological suggestion based on my literature that I have learned is that I have a very good slide for that to explain you. So here you can see in here that the selenium reducer, it needs molybdenum to make selenate reductives, and which ultimately in the periplasm of the microbes reduce selenate into elemental selenium. And based on the literature, I found that this molybdenum insertion into the microbes had been inhibited by high sulfate concentration. So it would be nice, because I already finished my project, but I'm saying that it would be nice that if I able to remove the sulfate first, then do the same process and see whether that microbes can reduce that into the 0.003. But I'm not sure that it can reach that point. But I'm saying that it's possible, that because in my system I reach to the on average 50 ppb, so it can possible to reduce furthermore to reach the EPA guideline, which is 3 ppb. So my suggestion would be to remediate to precipitate out the sulfate by using barium chloride, and then follow that same treatment and see whether it can reach to 3 ppb, which is guided by the EPA. Hope this answer will give you what you are
Okay,
seeking.
thank you for your explanation.
You're welcome. Okay. Mhm. Do you have guys any questions? So I'm happy to answer. Thank you so much, everyone, for your valuable time to see my hard work the last few years. And thank you so much for your valuable time. I know everyone is busy, and you guys came here to see what I have done the last few years. So thank you so much. And let me know if you have any question. I will be here in the chat box, or email me. I'll be happy to answer if you have any questions in future. Thank you so much.
Thank you, Anik. Yay.